Okay, so now let's calculate, say, expectation of S square actually. Okay, so expectation of S square we know that it's I equal to 1 to n xi minus x bar square and everything divided by n minus 1 times the expectation of x actually. Okay. So for the sake of simplicity, rather than writing this denominator again and again, let's multiply this n minus 1 on the other side. Okay. Expectation of s square, and let's calculate, say, the expectation of this sum I equal to 1 to n xi minus xi bar square. Okay. I mean, if you see this seems like a very familiar expression actually. Okay, so you can expect it to be even, what do you call, variance actually. Okay. So let's see that how it goes. So, I mean, one of a way could be that, okay, you solve this square, for example, and compute the expectation individually. So you're going to get three terms, xi square, x bar square, and then, you know, those three terms. And then simplify the expectations, and then calculate the expectation. But the other way is basically you can have various ways of calculating, doing the sum. So this is going to be the expectation of, say, sum. So let's play a bit. Can I do this, that if I add and subtract, for example, mu in this expression, and then I apply what do you call my square formula. So it's going to be the expectation of sum that goes from I equal to 1 to n xi minus mu square plus mu minus x bar square and minus twice of, say, xi minus mu times mu minus x bar. Okay, this is what that you're going to get. Alright, so if you now take the sum, so if I, for example, simplify this a bit more, so these two terms involve the index I. So this is going to be the sum that goes from I equal to 1 to n xi minus mu square, okay, while this term has no index. So summing up this expression is like summing up this number n times actually. So if I apply the sum onto this term, and there is no index in it, so it's like, okay, you have, say, I equal to 1 to n and a quantity that is a actually, for example, and a is some constant which does not involve any index a. So what does it mean? It means that you have to add, you are adding a n times. So obviously this should be an a. So similarly, now since this does not involve what you call any index, so you can say that this is going to be n times of mu minus x bar square and minus sum that goes from, say, I equal to 1 to n of this quantity. This quantity. But even if you see carefully, so if you take the sum of this quantity, in this quantity only this term involves index, while these two terms it does not involve index. So if I take this sum and put it here, okay, put it here, then in that sum 2 and a mu minus x bar are like appearing in all terms, so you can take them common actually, okay, so you can pull them out by distributive law. So So taking that sum and pulling this 2 times mu minus x bar out, so what you're going to get? You're going to get xi minus mu. Okay? You're going to get xi minus mu. So this is what that you're going to get. So if I simplify it a bit more, what would be this sum? Okay, so what would be this sum? So in this sum, I can, for example, multiply and divide, say, things by n. So if I multiply and divide this by n, so in other words, this would be equal to expectation of the first term is same plus the second term is same. Okay, the first term is same and the second term is same, and in the third term I'm writing, say, 2 minus mu x bar, and in this sum I equal to 1 to n. Okay, I am multiplying and dividing it by n actually. So if I take, say, xi minus mu and I divide it by n and I multiply it by n, so what are you going to get? Okay, what are you going to get? So let's go a little bit a step ahead. So the same term plus same term minus 2n mu minus x bar. Now if I take this sum and apply it on this, the first term, so it's going to be sum that goes from I equal to 1 to n, xi divided by n. But this is precisely x bar actually. This is precisely x bar. Okay. This is precisely x bar. No, we are right actually. We are right. This is precisely x bar. So x bar minus mu square and minus x bar minus mu. Okay, so one thing that I have made mistake. So if this is a plus b square, then this twice should be of the plus actually. So this term should be positive. This term should also be positive actually. And this should be positive as well. Okay. Now the first term, as I said, will become xi by sum xi by n is going to be x bar minus sum of the mu by n. So this is the term sum I equal to 1 to n and mu by n. So what would be the sum that goes from mu? You know, it's like adding this number mu by n times. So the sum would be n times mu by n. So n will get cancelled and you're going to get what we call mu. Okay. And now we are in good shape. I can even put these terms together, these two terms together, and I can say that this would be equal to the expectation of the first term plus second term. So I can multiply by -1, and I can say that this is 2n x bar minus mu squared. Okay. And now let's apply the expectation. Let's apply the expectation. So when you're going to apply the expectation, the first term is this. So the expectation of the sum would be the sum of the expectation of these quantities. So the first term will become, say, the sum that goes from I equal to 1 to n, expectation of say xi minus mu squared. Okay, and plus what would be the expectation of this term? So this is constant actually, so you can keep it as it is. So it's going to be n times mu minus x bar, and this is square actually. Okay, this is what that you're going to get. And by the way, by the way. Even if you carefully look at the third term and the second term, they are alike actually. So this is like plus n. I can also write this as x bar minus mu square, no problem. I can take minus 1 common, still this would be n times x bar minus mu square. And this is minus 2n times x minus mu bar square. So 1n will be cancelled with 1n and you're going to remain with this. So the second term will go away. Okay, the second term will go away. In other words, this is 2n times x minus mu bar square. This is n times x bar minus mu square. So remaining would be n actually. Okay. And now you're going to get this. So if I take the expectation of this term, you know, all these numbers are fixed and constant, so you're going to get precisely, not going to get the precisely same thing, but you will have n equal to the expectation of x actually, expectation of this. Okay. Now, what is expectation of xi minus mu square? Okay, so you can I can simplify this actually. Okay, so I can simplify this. So let's calculate, for example, say the expectation of xi minus mu square. So this is same as xi square plus mu square minus twice of the mu expectation of xi. Okay, this is what that you're going to get. You're going to get expectation of xi square plus mu square minus twice of, this is like a constant, so you're going to get expectation of 2 mu times expectation of xi. Okay. Now, expectation of xi plus mu square, and this will also become what you call mu square actually. Okay, this will also become mu square because the expectation of xi is mu. So the final term that you're going to get is xi square minus mu square actually. Now if you think about the variance of xi, so we know that the variance of xi is sigma square, but the variance of xi square is also expectation of xi square minus expectation of xi whole square actually. This is what it is. And if you see, this term is precisely same as this term. So in other words, this difference is equal to the sigma square. So in other words, this expectation is sigma square. So if this is sigma square, so summing up this sigma square n times, you're going to get sigma square. What is this quantity now? Expectation of mu minus x bar square actually. Okay, so the expectation of mu minus x bar square can also be simplified, but you can also call it that this is really the variance of x bar square actually. So expectation of mu minus x bar square is variance of x bar. This is what is the precise definition of the variance of x bar actually. Okay, so the variance of x bar. In other words, if you simplify this guy, you're going to get variance of x bar from previous calculation. So this will become n sigma square minus this will become n times the variance of x bar by definition. But we computed variance of x bar as n sigma square minus variance of x bar was n times of sigma square by n. So this n will cancel out and you're going to get n minus 1 times sigma square. Okay. So here is something very interesting. So on other side, you have n minus 1 expectation of s square, and here you get expectation of, so the n minus 1 times expectation of n square is equal to n minus 1 times the sigma square, so therefore the expectation of s square is really equal to sigma square. So what does this is telling you? Okay. So this guy or this thing is telling you that if you take your sample deviations, okay, sample variances actually, so S is representing the sample variances, okay. Now the expectation of that sample variance is equal to the variance of each individual sample point actually. So it shares, so sample variance shares its average value equal to what you call sigma square. In other words, if you have n data points which are independent of each other and identically distributed, so they have a mean mu and variance sigma square, and then you take, for example, the sample variance of it. So what would be the value of sample variance of that data? The sample variance of that data set is going to be equal to the same variance that you have for the initial, each data point. So it's going to share the value. So the sample variance on average is going to share the value with the each data point actually. Okay. So the variance of this expectation of the average value of the sample variance is going to be equal to the variance of all data points, which is sigma square actually. Okay. So on average, this sample variance will not change its value, and it will be equal to the sample or the variance of the each data point. So this is an interesting factor actually, which has kind of very interesting consequences. Okay. The reason for doing this example was to indulge into such calculations, because such calculations are important when you want to, for example, do this stuff with regards to the research actually. So that's a very good place where you used all of your previous, for example, results obtained actually about expectations and variances and covariances. So all these results are being used here. So it's important to use what you call such kind of, it's important to get into such kind of calculations actually. Okay, now let's move to another important quantity, which is called the correlation coefficient. Okay, so the covariance tells you that, okay, the two random variables are sharing, do they have a kind of a relationship between each other? In other words, positive or negative relationship. In other words, by a positive relation that, okay, if one increases, the other would also increase, and if one decreases, other would also decrease. Okay, and there can be, what do you call, different kind of such relation. For example, if you see that, okay, so if x and y, so one could be one of the relationship could be like this, that, okay, as x is increasing, y is also increasing actually. So you're going to say x and y has a positive covariance. Okay, so it could be the case that as x is increasing, y is decreasing actually. So here you have a positive kind of a covariance between x and y. Another thing could be that, okay, if x is decreasing, increasing, y is decreasing actually. So you have a kind of a negative relationship between each other. Okay. So this relation can be represented, what do you call, by a curve actually. But there is another thing that can represent kind of a strict relationship between x and y. In other words, x and y can also be, can have a kind of this kind of a relationship between them. That there is a linear relationship between them actually. So in other words, that y is like some ax plus b. So this is also possible that y and x are related in this manner. In other words, that as x is increasing, y is also linearly increasing with the same rate, what do you call, a. Okay. But if this A is negative, you're going to have also, what do you call, they can also have a relation that, okay, if x is increasing, y is linearly decreasing actually. Okay? So to know that between two kind of, relationship, two random variable or two processes, or random processes, what kind of relationship is there? One way is to find the covariances. So that reveals, that is going to reveal that basically how these two quantities are related with each other. But another interesting way is to check for the linear relationship between both actually. That are they linearly related with each other? So how can you know that two quantities are linearly related? In other words, that if either one is increasing, another is linearly increasing, or one is decreasing, another is linearly decreasing. So how can you know that whether such kind of relationship exists between two given random variable or not? The answer comes from what you call a quantity which is called the correlation. Okay? Correlation of the random variable x and y. Okay? And how do you define the correlation? So the correlation is denoted by rho xy, okay, and you defined it as that normalize the covariance by the standard deviation of x and the standard deviation of y actually. Okay, so this is what is the definition of correlation coefficient actually. Now, what is a good thing about this correlation coefficient? Covariance can be any big value, but if you standardize it with variance of x and variance of y, what we can prove actually that the rho of xy, okay, always lies between -1 and +1 actually. Okay, so it sits between -1 and +1. So it's pretty much easy to determine that two quantities are linearly related or not. So if sigma of xy, okay, are between say 0 and say 1, okay, so between 0 and 1, then you're going to say that yes, x and y are linearly related with some slope actually, okay, with some slope. So they are linearly related. In other words, that if one is increasing, the other is increasing actually, okay, and if rho of xy is exactly equal to 1, so you're going to say that, okay, they are perfectly correlated with each other. Okay, so they are strongly correlated with each other actually. That if one is increasing at a particular strength, if x is increasing at a particular strength, y is also increasing at the same particular strength actually. Okay, and if the rho of xy is a number between -1 and 0, you're going to say that yes, x and y are related linearly, but they are related linearly, they are negatively related with each other actually. Okay, and if rho xy is -1, so you're going to say that they are strongly negatively related. They are perfectly negatively related actually. And another thing that this tells you that rho of xy, if the rho of xy is 0, then this shows that x and y are unrelated actually. Okay? In other words, that x and y are not linearly correlated actually. Okay? So they are not correlated, they are not putting any impact on each other in the linear manner actually. Okay, this is what. So this is kind of computing the correlation for the, what do you call, random variables x and y is kind of a test to check that whether two quantities are linearly related with each other or not. Okay. But this does not reveal actually that, okay, that if they are not linearly related, they will not also be non-linearly related actually. So maybe, the two random variables are not linearly related, but the covariance between x and y are positive, so they kind of follow a kind of a, what do you call, a curvy fashion in which as x is increasing and y is increasing. Okay, so this computation of correlation kind of is a test for that whether the two quantities are linearly related or not actually. Okay, so this plays a pivotal role in science actually. Okay, you can also check that it's not difficult to see that, you know, why these two quantities are, why this correlation coefficient lives between, for example, these two numbers, say positive 1 and negative 1. For example, I can take one of the side and I can show that y, say the correlation coefficient is less than or equal to plus 1. For example, so for example, if you take the variance of say two random variables, say x plus y, but x divided by the standard deviation of x plus y divided by the standard deviation of y, okay, compute the variance of it. So I know one thing for sure, that variance is always non-negative, so it's not a negative quantity. So let's compute this variance. So if you're going to compute this variance, so the variance of sum is going to be equal to the variance of x by sigma x plus the variance of y by sigma y, okay, and minus twice of the covariance of x by sigma x, okay, and plus y by sigma y. Okay, sigma. This is what is going to be. It is going to be, okay, the sum of the two variance of two random variables. I don't know whether they are independent or not, so therefore you have to add this covariance actually. So what would be this quantity? So this quantity, so sigma x is like a number, you can pull it out, so it's going to be sigma x square times the variance of x. So the variance of x is also sigma x square actually. So it's going to be sigma x square over sigma x square plus, I can pull this 1 over sigma out, so 1 over sigma y square, and the variance of y is again sigma y square. Okay. So by the property of the covariance is, I can pull, if the covariance, you have the covariance of say ax and say by, you can pull out these numbers and simply compute the covariance of x. Okay, this is what that you're going to get. So you're going to have minus twice of say twice divided by sigma x and sigma y times the covariance of xy. Okay, but the covariance of xy divided by sigma x and sigma y is really the precise definition of the correlation. So this means that